Okay, so let's continue our discussion about the quantum harmonic oscillator. We said that our goal is to solve this equation where the Hamiltonian operator involves the kinetic energy and the potential energy for the harmonic oscillator. So we said all these are operators, right? Because it's the quantum, we're talking about quantum harmonic oscillator. Now, our goal is to solve the time-independent Schrödinger's equation, is to solve this equation here, right? Which, if we write with that potential, is this part involving the kinetic energy plus the part involving the potential energy equals to energy psi. That's what we want to solve. But before we reach that point, let's discuss and let's study this Hamiltonian a little bit more. One, there are two ways to solve this equation. One method to solve this is known as the power series method. Okay, and the other one is the algebraic method, very elegant. So power series method is one, and the algebraic method is another way. And this is the one that we are going to start discussing. Very, very elegant method, very smart. And to understand the procedures involving this method, we are going to start by analyzing a little bit closer, having a closer look at this Hamiltonian. Okay, so look what I'm going to do. I'm going to start by writing this Hamiltonian like this. I'm going to put this 1 over square 2m in front of everything. And now inside this bracket, I have the p square and m square, omega square, x square. Okay, so everything inside the bracket is squared. And why is this special? Well, because that gives us an idea. Now we are motivated by something that you already know, which is the following. These are all operators, but let me make a parenthesis here for something that you already know. Suppose we have two numbers, okay, just two numbers, u square plus v square. Something that you already know is that you can factor these numbers. You can write it like this, iu plus v, and the other one minus iu plus v. You know that these two things are the same, right? When we multiply these two terms, we get the u square. Then we have the cross terms. I'm going to mark them in orange. So these are the cross terms, but you know that they cancel. I, U, V, and minus I, V, U, you know they cancel. So I'm going to cancel them. And the last one is this one. So it's the V square that we have here. Okay, so you know about that. So motivated by this, we are going to try to factor this term. Well, let's see. If I just follow what we wrote on the right side, I'm going to try the following. I'm going to try this IP plus M omega X, and the other term, I'll try to use minus IP plus M omega, oops, I said X and put square, no? X, and then X. Okay, just following what we wrote here. Oh, but don't forget there is this 2m here. Okay, so let's put this as a square root of 2m. And so when we multiply the 2, we get that 2m. Very good. And I'm going to give names to these things, so I don't need to keep rewriting this whole long term. I'm going to call this one on top an A minus, and this one at the bottom, I'll call it an A plus. Okay? There is one more thing that I'm going to add to this story, just because I already know what we are going to move towards. I'm going to put an h bar omega inside the square root. I know where we are heading towards, and you will see why I added this to the story. But you see what we are trying to do. We are trying to rewrite this Hamiltonian using some product of this kind. Let's see if we can. Okay. Well, we cannot forget that we are playing with operators. And so let's always remember these hats here are telling us, well, these are not numbers. These are operators. Remember what this P is. It's a derivative. So things are not as simple as numbers, right? Very well. So what we are going to do is, we said we wanted to see if we could write that Hamiltonian using these products of this A minus and A plus. Well, let's start playing with that. So I'm going to start writing this A plus, A minus. Okay, so I'm just copying what we have above. Well, this whole term here we can put in front because it constants from both sides, no? So 2m and h bar omega coming from both sides. Now I'm going to copy here what we have in the numerator of the A plus, just copying what is above. And now from the A minus, which is I e plus m omega x. Very good. Well, let's continue. So here we have this number, and then we go. This term with this, well, we said it's b squared. Okay, now let me pick this other one. And then is m squared, omega squared, x squared. So this part looks exactly what we have here. Huh? But let me also write the cross terms. This and this. Let's write them. So from this first one, we have minus I didn't mark them correctly, right? Let's do this properly. So I'm picking the cross term, so it's this one with this, and this one with this. Okay, so let's write them. So the first one is minus I. Oh, then everything is constant, I'll put in front. So minus I m omega, fine. And then we have P with X. Let's see the next term now. This term here. So again, we have plus I m omega, and I'm looking at this one. So X with P. X with, and here comes something very, very important. You could perhaps already anticipate. These guys, we cannot cancel because here we have derivative in front of x. Well, here we have derivative behind x, and so after x. So these two things are not the same. It's very different from numbers. Now, when the order doesn't matter. When we are playing with operators, the order does matter. We cannot cancel these guys. We have to keep them. Okay, so let's rewrite what we got. We have a plus, a minus. Very good, equal to. Then we have this 1 over h bar omega, and I'm going to write just as we had above for the Hamiltonian, p squared plus m squared omega squared x squared with that 2m. So I put it like this because this is exactly what we had above our Hamiltonian. But as I said, this term here, we should not cancel. So let me rewrite it entirely. So we have, I'll start with the positive, plus I m omega, this is in both terms, and we have x p minus px and everything that is in the denominator. So I'm going to put here 2mh omega. So you see that sometimes I don't put the hat, but you know that there are hats everywhere. Yeah, hats everywhere. Very good. So what are we finding? Well, we have A plus A minus gave us Hamiltonian divided by that h bar omega. Okay, fine. And we have the other term. Let's see what we can cancel. There is mass here, there is omega here, correct? And then we have plus I over 2h bar. And look how I'm going to write this term. This is a notation that I'm going to use with this bracket, x comma p. This notation is what we call commutator. Whenever you see this notation between any two entities, okay, so this notation, what does it mean? A multiplied by B minus B multiplied by A. Okay, exactly what we see here. Okay? So this is the commutator. We say that these two entities, they commute. Okay, so the term is AB equals 0 if A commutes with B. What does it mean? That this order doesn't matter. And we say that they do not commute if this is different from 0. So if you learn linear algebra, you know that matrices usually do not commute, that the order of the multiplication of matrices matters. So, and using the order of the two operators, the order that we use for the operators matter. That's what we are showing here. But I need to tell you now, I'm saying that these two things, x and p, do not commute. Cannot just say that this is 0, but what we need to find now is, okay, it's not 0. What is it? Okay, so we are going to start studying now what is the commutator between x and p. And to help us with that, I'm going to put here an auxiliary function of x. You will see how it helps us. So let's just write, we have xp with that function, right? And we have minus px on that function. This, what we wrote here is just the property of the commutator. Okay, but what is P? Well, P is that h bar over I and the derivative in x. All right, so then what we have here is x, a constant we can put in front, it doesn't hurt. No, it's just a number, h bar I, and the derivative of that function of x. Okay, and the next term we have minus h bar over I and the derivative, but the derivative of everything that is to the right of it. So the derivative of x and f. And so let's continue with this. H bar over I. So this, all of the terms have. Then we have x, derivative of f. Then we have first the derivative of x, which is 1. So we have 1 multiplied by f. And then we have the derivative of f. So then we have minus x derivative of f. All right, this cancels, but this survives. All right, and there is a minus sign here with 9i in the denominator. I can write this as positive if I bring the I to the numerator, right? So we end up with this. So this function, as I said, was just an auxiliary. Okay, so with this, we now conclude what is the commutator between x and p? I h bar. This is what we'll have to put there where we had put our question mark, I, H bar. Okay, all right, so let's get some space here and write what we have there, right? So let's get some space and continue here. So then what we have is A plus A minus is the Hamiltonian that we were after, but with this H bar omega. And then here, let's see what we have. We have I with I. So this gives us a -1. We have H bar in the numerator and H bar in the denominator, so we can cancel it, right? So we end up with -half. Very good. So now we have our Hamiltonian. Let's write it. The Hamiltonian is equal to what? A plus A minus plus half. So we finally get that the Hamiltonian is H bar omega, A plus A minus plus half. That's the correct way to write the Hamiltonian in terms of these new operators that we introduced, which are the operator A plus and the operator A minus. Okay? But you see that the order, now you have to, you should be very careful about this. The order between operators matters. And so we started our game here with this order, A plus, A minus. If you go through the same procedure, but in opposite, let's put it here. If you go A minus, A plus, and I leave for you to do this, and your book does this case, A minus, A plus, you will see that you're going to arrive something very similar. Hamiltonian with that H bar omega, but then what comes next here is plus half because the order matters. Okay, and then you're going to find the Hamiltonian is for A minus A plus with a minus sign here. Well, let's put everything together, the different ways that we found to write our Hamiltonian. We started with this way. We said, well, we can write the Hamiltonian as p squared over 2m plus half m omega squared x squared. Okay, so this is one way using the potential for the harmonic oscillator. Very good. But after introducing this operator A plus and the operator A minus, we found out that we can write this Hamiltonian as equivalent to what we have there. We can also write this Hamiltonian as H bar omega with A plus A minus plus half. This is exactly the same thing as we wrote above, just a different notation using these new operators. And we can also write it as H bar omega, A minus, A plus. Exactly the same thing, minus sign, careful. The order of the operators does matter. Okay, but these three things that you see here, they're all the same, the Hamiltonian of the quantum harmonic oscillator. Okay, let's summarize what we've seen in terms of commutators. Let me get some space here. We said that the commutator between x and p, we found it above, is I h bar omega. Correct. Well, I could ask you, how about the commutator of p with x? It's very simple. Open the commutator above, and everything that we get for this new commutator is the sign that changes. So this is going to be minus I h bar omega. Okay, so you can check that. Okay, so these are the commutators between x and p. Correct? So this is what we call the canonical commutation relation between X and P. Very important. All the discussion that we had about uncertainty principle in chapter 1, you will see later when we move to chapter 3, that that the relationship comes from the fact that position and momentum do not commute. Comes from this. You will see it later, okay? But this is a very important relationship. So we found then the commutator between position and momentum. Good. How about the commutators between these two new operators that we introduced, the A plus and the A minus? Can we find that? Okay, so my question now is, what is the commutator A minus A plus? Can we find that? Well, look, the easiest way to do that is using exactly these two equations that you see. How? Look, what I'm going to do is, I'm going to put a minus sign in this equation, okay? And I'm going to add these two equations. Well, let me rewrite. So if I put a minus sign on the top one, we'll have minus Hamiltonian equal to minus, no, because I multiply multiply this minus 1 to that whole equation, A plus, A minus, and minus H bar omega over 2. So this is equation on the top. Equation on the bottom, I'm not doing anything, so it's just what we see there. Very good. I'm going to add these two. If we add these two, this cancels, right? This becomes 0. And then what we have for the next terms, careful, operators very often do not commute, so I cannot cancel these two. What I'm going to write here, H bar omega with A minus A plus, and that's minus sign here, minus A plus A minus. Good. And now this last term, these are really numbers, but both have the same sign, right? So minus H bar omega. Okay, so what we got here, well, you see that the H bar omega can cancel, right? So we have A minus A plus minus A plus A minus equal to 1. I pass this to the other side. So equal to 1. So the question that I had asked, what is the commutator between A minus and A plus? Well, now you know, it's just 1. And if you then check, oh, okay, and what is the commutator between A plus and A minus? Well, we already discussed about, right? It's just minus, it's just the opposite of what we have above. And you can see this easy now. So the commutator here is A plus, A minus, minus, A minus, A plus. What is that? Well, look at the top. It's exactly the same thing as we see above, with a minus sign. Okay, so I'm going to interrupt this video here. This is the beginning of this section. This section 2.31 is not the end yet. We just arrived at the equation. If you go to your book, equation 2.57 and equation 2.58. Okay, well, the equation 2.58 is then the Hamiltonian that we want to solve. Oh, sorry, the Schrödinger equation that we want to solve. How are we going to write this equation? Well, now that we have the Hamiltonian in terms of these new operators, we are after solving this equation. Okay, either this way, if you prefer, you can also write it with the inverted order of the operators, but careful, don't forget, then you need a minus sign here. Okay, so this is what we are going to start studying in the next video, because this is already long enough.